Welcome back, everyone. Let's go and have a look at some more typical questions that we can get asked as part of the electrochemistry exam type questions. We might not cover everything, but we're going to try and cover as many interesting aspects of revising questions related to electrochemistry. So here we go. Consider the electrochemical cell below, and what you'll see is that we've got one cell. So there's the one container. We've got a concentrated solution of copper chloride in the solution. So we've also got a battery or a power source. So I'm sure that you'll be able to see from that that this is an electrolytic cell. It's unlike the galvanic cell. In other words, it's taking electrical energy and it's making and changing, producing chemical potential energy. So it's making a change in terms of chemical potential energy. It is not spontaneous, and it uses up energy to make this chemical potential energy in the form of a chemical reaction, where there's a change in the nature of the chemicals that we started with. So very important that you be able to identify these cells. Notice there's no salt bridge, there's one container, and there's a battery. There's no voltmeter in this scenario. Let's go to the next question, and you'll say, interesting, what type of power source is there? Is it an AC or a DC electrical power source that is used to drive this? Now let's think about that for a minute. If we had an AC power source, then that means that the sign of each of the electrodes would change continually. So at one moment this would be positive and this would be negative, and a few seconds later this would be negative and that would be positive. Well, that would be very confusing. And we know that it's the polarity of the electrodes that actually makes the reactions happen. If we kept on changing them, we would get different reactions happening at each of the electrodes all the time, and they would cancel each other out. So it can't be AC. This has to be DC. And so let's bear that in mind, that this is direct current. We're wanting a continual path of movement of charge in one direction. Now, I don't know if that's going to be the movement of positive charge or negative charge, but we want it in one direction, which is direct current. So the next question is a little bit more interesting, because it now tells us that this cell is used in the refining of copper. One of the electrodes consists of impure copper. When an electric current passes through the cell, the mass of electrode D increases. Is the electrode D the cathode or the anode? And we're asked to write down the relevant half reactions to support the answer. So there's a whole lot of information being given there, and we just need to recap it and make sure that we've recognized it and annotated it on the graph, on the diagram. It's always good to add information to the diagram. So the first thing I'm going to do is I'm going to take information from the question and recognize that there's an increase of mass at electrode P. So if there's an increase of mass at P, we also were told, there was one other thing. This is the refining of copper. One is impure copper and the other must be pure copper. So we've got two electrodes, one impure and one pure. We also recognize when we're refining copper, the pure copper is going to be where all the copper is going to be deposited. So I'm going to say P is pure copper. And that means that copper, 2+ ions here, are going to be changed into copper metal. That deposit is going to cause the increase in mass. And so if I had to write down the half reaction, we're going to say copper 2 plus ions plus 2 electrons are going to form copper metal. Now, you could go and look that up on the standard reduction potentials, but it's not necessary. You know that you've got copper, pure copper, and you've got copper ions in solution. It can only be the reaction between copper and copper ions. So it's not difficult to see that this is the reaction. And if you look at it, it's a gain of electrons that is producing a deposit of copper. This is a reduction reaction. And reduction always takes place at the cathode, because we remember that we've got to look for the red cat. So, very interesting. For this answer then, we've got the relevant half reaction. We recognize that this is the cathode. So let's just put that in. So we've got it. And more important to recognize, this, because it's attracting the copper ions, must be negative, which means that terminal must be positive. Now, I don't know if they're going to ask questions about that, but I just like to add in the extra detail. If you're not sure why it's positive, let's just think that through, or why it's negative. Remember, for the ions to be attracted to the electrode, they've got to be attracted to the opposite charge than what they are. So the copper ions here are positive, and they're going to be attracted to the opposite, which is negative, to form this reaction where they're going to gain the electrons and they're going to form copper. Right. I think that was quite an interesting question, and I hope you've enjoyed looking at that. Remember, when we're dealing with these electrolytic cells, it's a separate question to the galvanic cells that you'll find in the final exam paper, but there are lots of different types of diagrams, because there's not a standard diagram for electrolytic, depending on how it's being used. We're not going to be able to cover all of them, but in this case we've done one of them, the electrorefining. So here's an interesting question about this impure copper. So remember, the impure copper was this side, and we're told that there are zinc impurities. So inside here there's copper mixed with zinc. We know that there are copper ions in the solution, and we know that the copper is being deposited over there like that. We know this is negative, this is positive. Let's add on. So there's an initial reaction that's taking place. They tell us that the zinc impurities are going to form zinc ions. So zinc goes to zinc 2 plus 2 electrons. Now, how is that actually happening is just because zinc is a very reactive metal. If we look at the standard reduction potential table, we'll see that zinc is a stronger reducing agent than copper. Let's go and have a look at that, because that's exactly what they're asking in the next question. So if we run our finger down, remember, reducing agents on the right-hand side, we find that zinc is over here and copper is below it. Can't fit them all onto one table, but copper is down below it. So even naturally, we're going to find that zinc will form zinc 2 plus ions, and it will force the copper ions in the solution to gain electrons and to make copper go back. So the zinc ions in this solution are forced to become zinc 2 plus, and it's taking some of those and making the copper be deposited back onto Q as well. Even though when we connect these, the copper ions don't really want to be attracted there, because that's positive. Copper's ions are going to be repelled. But the zinc is being oxidized there, maybe even before we turn on the cell. So now we're competing zinc ions to copper ions. We're going to say, which of these are going to be attracted more to the negative terminal? Well, we've got to understand if they're going to undergo a gain of electrons, we've got to compare their oxidizing ability. So let's go back to the table, because that's exactly what they're asking. They say the relative strengths of the oxidizing ability, why zinc ions will not influence the copper deposit over here. So if we look at the table, you will see that zinc is very high up on the table. Look at the value, -0.76, whereas if you look at copper, it's one of the oxidizing agents. It is a reading of plus 0.34. So zinc is a much weaker oxidizing agent. Zinc, weaker oxidizing agent. In other words, you're going to need to give zinc a lot more energy to give up its status as a zinc ion in the solution. It doesn't like to become zinc metal. It's too reactive. So we would be able to say in the answer to this question that in fact what's happening is that we're seeing that copper is a stronger oxidizing agent. So at least the copper ions are a stronger oxidizing agent. They will require less potential difference to be deposited on, and we can control the potential difference. Remember, this is a non-spontaneous reaction, and we'd be able to keep the potential difference low across the electrodes so that zinc isn't deposited. In that way, we ensure that there's a perfectly 100% deposit of pure copper on the electrode. So that's been quite interesting. Right, let's just wrap up the lesson by looking at a quick summary. Recognize that we've done much of this before. A galvanic cell, remember, it's taking chemical potential energy and converting it into electrical potential. Most important, oxidation is always at the anode, reduction always at the cathode. And remember that the salt bridge is the unique thing about the galvanic cell. It completes the internal circuit and allows a free flow of anions to the anode and cations to the cathode. Remember as well that for the galvanic cell, we can calculate the E0 of the cell, where we say E0 of the cathode minus E0 of the anode. And that will give you a positive value. It will always be positive because it is a spontaneous reaction. We're not adding any energy to it. So it's very important that when you do that reaction, you can calculate it and you can see how it works. If you go to the electrolytic cell, recognize that energy transfers from electrical energy into chemical potential energy, where the E0 of the cell is negative, it's non-spontaneous. We're needing to put energy in, whereas the oxidation reaction always takes place at the anode, even if it's electrolytic, and reduction always takes place at the cathode. So as we conclude now this whole summary on revising electrochemistry, I hope you've enjoyed it. Please study hard, and I wish you the best for your tests and exams. Bye for now.